Have you ever stopped to wonder how every single tweet, every photo you upload, or every online order you make gets its own unique ID, like instantly? We're talking about billions of things being created all over the world, and each one needs its own name. Today, we're going to pull back the curtain on the brilliant engineering behind this massive global naming system.
So how do you actually do that? Think of it like a global ticketing system, but not for a concert, for everything happening online. Every single action needs a unique ticket number. Now, how do you hand out those tickets from thousands of different booths all around the world in milliseconds without ever giving out the same number twice? That's the huge scale of the problem we're talking about. On a single computer, this is a piece of cake. You just count up, 1, 2, 3, and so on. But when you're dealing with a massive distributed system with servers dotted all over the globe, well, that's a whole different ballgame. How do you get thousands of machines to agree on what the next number is without them constantly chatting and slowing everything to a crawl? This is where it gets really complex. Okay, so before we can even dream of building a solution, we need to set some ground rules. What does the perfect ID even look like? Let's put together a wish list of all the must-have features for our system. First off, and this is the big one, our IDs have to be absolutely unique, no exceptions. They also have to be numbers only, no letters or weird symbols. And they've got to be small enough to fit into 64 bits of data. Now, this next one's crucial. They must be sortable by date. An ID created later has to be a bigger number than one created earlier. And finally, this whole thing needs to be ridiculously fast. We're talking about generating over 10,000 IDs every single second. All right, we've got our wish list. Now it's time to put some of the usual suspects to the test. Let's line up 3 common approaches and see how they stack up against our really tough requirements. First up to the plate is a pretty clever trick from the database world called multi-master replication. The basic idea is to take a standard database feature, auto-incrementing numbers, and figure out how to make it work across a bunch of different servers at once. So here's the trick. If you have 2 servers, you tell one to only create odd numbers, 1, 3, 5, and the other to only create even numbers, 2, 4, 6. Pretty neat, right? It avoids duplicates. But there's a massive problem. An ID of 2 could be created after an ID of 3, which completely shatters our ordered by date rule. And for what we need, that's a total deal breaker. And this right here is the fatal flaw. If the IDs aren't sortable by time across the whole system, we lose a critical piece of the puzzle. Just imagine trying to read a conversation online where the replies show up before the original post. It would be chaos. So this contender is out. Okay, let's move on to contender number 2, the Universally Unique Identifier, or UUID. You've probably seen these things. They're those super long strings of letters and numbers. And they're designed to be unique, not just on your computer, but across the entire planet. So how do they work? Well, each machine just generates a gigantic random number, and the chance of 2 machines ever picking the same one is practically 0. But for what we need, UUIDs fail on so many levels. They've got letters, they aren't ordered by time, and they are way too big for our tiny 64-bit requirement. And this is the most obvious failure. At 128 bits, they're literally twice the size we can afford. It's like trying to park a giant truck in a parking spot built for a motorcycle. It's just not going to work. And trying to make it fit would waste a ton of storage. So contender number 2 is down for the count. All right, our final challenger takes the complete opposite approach. Instead of having every server make its own ID, what if we had one central server that just handed out numbers? Like a ticket dispenser at a deli counter. The logic is super simple. One server, one perfect stream of ordered numbers. It works great. Until it doesn't. What happens if that one server crashes? The entire global system grinds to a halt. No new IDs can be made. Nothing. And that is the knockout blow, a single point of failure. In a system that needs to be available 24/7 for millions of people, this isn't just a risk, it's a guaranteed disaster waiting to happen. So there you have it. 3 contenders, 3 big failures. So after watching 3 popular methods just completely fail, what's left? Well, the answer is a truly elegant solution that was pioneered by Twitter, and it's called Snowflake. It meets all of our requirements, not by trying to count bigger or faster, but by thinking a whole lot smarter about how you build an ID in the first place.
The absolute genius of Snowflake is the simple principle of divide and conquer. Instead of treating the 64-bit number as just one big integer, it breaks it down into smaller, meaningful chunks. Each little piece tells part of the story of where and when that ID was born.
So let's do it. Let's crack open a Snowflake ID and actually see what it's made of. We're going to break down this 64-bit number piece by piece. Think of this like a digital recipe. The first bit is just a placeholder. Don't worry about it. But the next 41 bits, that's the secret sauce, a timestamp measured in milliseconds. This is what makes the IDs perfectly sortable by time. The next 10 bits tell us exactly where the ID was created, which data center and which specific machine in that building. And those final 12 bits, that's a super high-speed counter for when things get really busy. And that 12-bit sequence number is so important. It means a single machine can generate 4,096 unique IDs in the exact same millisecond. This is what gives the system that incredible speed we needed.
And those 5 bits for the data center ID? Well, they allow the system to scale up to 32 different physical locations anywhere in the world without any risk of them creating the same ID. This creates a truly distributed solution that completely avoids that single point of failure we were so worried about.
Now, the Snowflake solution is brilliant. It really is. But it has this fascinating limitation baked right into its design, a ticking clock, if you will. See that 41-bit timestamp, the very heart of the system, can't just count forever. It has enough room to count milliseconds for about 69 years from whatever start date they chose. After that, it runs out of space, it overflows, and the system would need an upgrade. It's a pretty cool reminder that even the most elegant engineering solutions have a shelf life. So let's just recap the genius of this. It's really just a simple 3-step recipe. First, you anchor the ID in time, which makes it sortable. Second, you make it unique in space by adding its location. And third, you add a rapid-fire counter to handle huge bursts of activity, time, space, and speed, all packed neatly into 64 bits. When you get right down to it, the Snowflake ID is more than just a clever number. It's a perfect example of the divide and conquer strategy. It takes this massive, seemingly impossible problem and solves it by just breaking it down into smaller, smarter pieces. And that kind of makes you wonder, doesn't it? What complex problem in your world could be solved if you just found a way to break it down?